THCCODCGNAL, it began like any other quiet night in the world's observatories. A calm hum of machinery, the soft chatter of data streaming through digital pipelines, and the silent watch of the cosmos. Then, at exactly 3:47 a.m. Eastern Time, that silence shattered. Across 3 continents, radio telescopes lit up in unison, registering something no one could explain. A pulse, brief but unimaginably powerful, coming from the direction of the Andromeda Galaxy, our nearest galactic neighbor. Within seconds, the automated alert systems at the Keyam Observatory in Canada began to flash warnings. At first, operators thought it was an error, a sensor overload, maybe a spike of terrestrial interference. But as they scrambled to check the instruments, a chilling realization spread. The same spike had just been recorded in New Mexico, Australia, and South Africa, all at the same exact time stamp. The pattern wasn't local, it wasn't human, it was astronomical. The data, once compiled, revealed something extraordinary. The signal wasn't just a burst. It was 50 times stronger than any fast radio burst previously recorded from that region. Even more unnerving, its frequency signature matched another event, one that had occurred 18 months earlier, also from Andromeda. That earlier event had been cataloged as FRB2401 a short, bright flash lasting just milliseconds, dismissed as a likely magnetar outburst. A curiosity, yes, but not a revolution. Until now, the second wave changed everything. Within minutes, NASA's Deep Space Network was fully mobilized. The 70-meter dish at Goldstone, California, swiveled toward Andromeda's coordinates. Similar arrays across the globe followed. The data poured in, 3 full seconds of sustained, organized radio emission. To put that into context, in radio astronomy, 3 seconds is an eternity, long enough for patterns to emerge, long enough to show intention. And patterns were exactly what they found. NASA's latest AI analytical system, a neural network architecture originally adapted from DeepMind's protein folding algorithms, was repurposed to comb through the incoming data. It was designed to find order in chaos, subtle symmetries, mathematical ratios, hidden periodicities, things too intricate for human pattern recognition. What it uncovered froze the entire analysis team. The polarization of the signal, the orientation of the radio wave's oscillation, wasn't random. It flipped rhythmically every 200 milliseconds in a cycle of perfect precision. In natural sources like pulsars or magnetars, polarization changes are erratic, shaped by turbulent magnetic fields. But this was mechanical in its regularity, almost engineered. Every telescope confirmed it. The signal wasn't just strong, it was structured. Across NASA, the European Space Agency, and the SETI Institute, scientists scrambled to compare notes. Within hours, all the independent confirmations aligned. Same source, same structure, same inexplicable rhythm. Andromeda, sitting 2.5 million light-years away, had just spoken. The implications hit fast. Whatever produced this pulse did so 2.5 million years ago. Back when early human ancestors on Earth were barely learning to use stone tools. Yet here it was, arriving now, in perfect coordination, stronger than any previous burst, carrying with it a pattern that defied every known law of astrophysics. For the first time since humanity began listening to the stars in 1960, the AI systems trained to classify cosmic phenomena simply responded with unclassified anomaly. The data looked unlike anything in their archives. It wasn't a pulsar, it wasn't a magnetar, it wasn't a black hole flare or a supernova echo. It fit no category in the vast library of cosmic signatures scientists had built over 6 decades. And that's when something even stranger happened. At 3:51 a.m., 4 minutes after the pulse arrived, the Earth's magnetic field suddenly flickered. Every global monitoring station, from Alaska to Antarctica, registered a simultaneous, measurable disturbance. For 8 seconds, the magnetosphere, our planet's invisible shield against solar radiation, compressed inward by nearly 2,000 kilometers, then snapped back. Initially, Experts assumed it was a solar flare, a routine coronal mass ejection from the Sun that sometimes triggers geomagnetic storms. But when NASA's Solar Dynamics Observatory checked, the Sun was perfectly calm, no flare, no plasma surge, no abnormal solar wind. The space weather data was pristine. That left one possibility: the timing was a coincidence. Except it wasn't. The disturbance began exactly 4 minutes after the signal from Andromeda reached Earth. The delay was the precise amount of time it would take for a high-energy particle wave, traveling near light speed, to traverse the distance from the upper atmosphere to the magnetosphere's boundary. A radio signal from another galaxy shouldn't, by any stretch of known physics, have any measurable interaction with Earth's magnetic field. Radio waves pass through magnetic fields effortlessly, the way light passes through clear glass. Yet the correlation was undeniable. The timing matched perfectly. NASA's Goddard Space Flight Center dug into the archives and found something even more chilling. A similar but smaller disturbance had been recorded 18 months earlier, roughly 8 minutes after the first Andromeda signal. It had been dismissed as background noise at the time. Now, in hindsight, it looked anything but random. That's when the internal alerts went out. NASA called an emergency scientific briefing, looping in every major radio observatory and astrophysics institute on the planet. The language used in those first internal memos was cautious but tense. Terms like statistically correlated, non-terrestrial interference unlikely, and potential unknown coupling mechanism appeared in reports. In plain English, the signal from Andromeda seemed to have interacted with Earth itself. Scientists ran the numbers. The brightness of the signal, measured at 140 Jansky at Earth's surface, was staggering. For comparison, the brightest fast radio burst ever recorded before this one peaked at 3 Jansky, from a galaxy a billion light-years away. Applying the inverse square law, where intensity decreases with the square of distance, the source in Andromeda would have needed to release over 500 times more energy than any previously known event of its type. In 3 seconds, that burst emitted more radio energy than our Sun produces in an entire hour across all wavelengths. That kind of energy output is almost beyond imagination. Dr. Vikram Patel, an astrophysicist at MIT's Kavli Institute, reran the calculations multiple times. Each time, the numbers held steady. He even suspected his software might be glitching. It wasn't. The readings were consistent across every global station. Only 2 known astrophysical events can release that much energy in such a short span: colliding neutron stars and hyperflaring magnetars. But both of those are one-time events. Neutron star collisions destroy the system permanently. Magnetars can flare, yes, but not twice with identical precision, and certainly not from the same coordinates 18 months apart. Whatever this was, it had repeated, a cosmic echo from the same location. As NASA's AI continued dissecting the waveform, it discovered something buried deeper within the data, an internal pulse pattern. The signal wasn't continuous. It was segmented. Each pulse lasted exactly 43 milliseconds, followed by 86 milliseconds of silence, then 172 milliseconds, then 344, doubling each time. A perfect geometric progression. That's not random. That's mathematics. In digital systems, exponential spacing like that is used for error correction, a way to encode information reliably over long distances, ensuring the message stays intact despite interference. To see that kind of structure in an astrophysical event was, frankly, unthinkable. Sarah Brennan from the Breakthrough Listen project compared it against every known catalog of pulsar and magnetar activity. Natural phenomena always contain irregularities, slight timing drifts, random phase noise. But this, it was clockwork. Too clean, too stable, too perfect. The longer scientists stared at the spectrogram, the less it looked like a natural emission, and the more it resembled a transmission. Still, NASA refused to jump to conclusions. Extraordinary claims demand extraordinary evidence, and the idea of an engineered signal from another galaxy is the most extraordinary claim of all. But quietly, behind closed doors, the discussion had already begun. Could this be evidence of an artificial source? Or were we seeing some new kind of physics, something no telescope had ever captured before? Perhaps a yet unknown mechanism of space, time, a natural process so complex it mimicked intent. In the data rooms of JPL, where walls are lined with humming servers and the soft glow of monitors reflects on sleepless faces, that question hung like static in the air. Scientists zoomed into each frame of the signal, tracking polarization shifts, amplitude modulations, phase rotations, searching for meaning in the noise. Every discovery deepened the mystery. The AI's next report came with a warning tag: non-stochastic periodicity detected. Probability of natural origin, 0.05%. A probability that low doesn't prove intelligence, but it does imply something non-chaotic, something organized. And then came the last finding that night, one that stopped every conversation cold. When the AI plotted the polarization shifts and pulse intervals in a 3D model, it generated a pattern resembling a geometric lattice, similar to a wave interference grid. Except the alignment corresponded perfectly to mathematical constants ratios found in Fibonacci sequences, harmonic intervals, and even the golden mean. Coincidence? Perhaps, but nature rarely arranges chaos so beautifully. At dawn, as the sky over the Mojave Desert brightened, NASA's chief astronomer addressed the assembled team. Her voice trembled slightly when she said, "We've verified the signal. It's real, it's structured, and it's stronger than anything we've ever seen." No one clapped. No one smiled. The room was silent, because they all understood the implication. If the signal was natural, it meant a new force of the universe had just revealed itself, something capable of bending known physics. If it wasn't natural, if it was deliberate, then someone or something 2.5 million light-years away had just spoken, and that realization carried a weight that no scientific training could prepare them for. Every telescope on Earth was now pointed toward Andromeda. Every supercomputer was reprocessing the data. And every scientist who stared into that wave pattern knew one thing for certain: the universe had just changed. Because when the cosmos speaks, it never whispers twice. THEDURBNCE the morning after the second signal hit, the world's observatories were no longer quiet. Scientists who had gone home to sleep came rushing back through glass doors with half-buttoned shirts and coffee, stained notebooks. News had already begun to leak. An anomaly, detected from Andromeda, something not in the models. No one outside NASA or the Deep Space Network yet knew what that meant, but inside those corridors, the tone was urgent. Every major array, Kesham in Canada, Parkes in Australia, the Very Large Array in New Mexico, Meerkat in South Africa, all confirmed the same results. The source was fixed. The coordinates pointed straight into Andromeda's spiral arm, near its luminous galactic core, a point of light 2.5 million years and 2.5 million light-years away. But now, for the first time, there was something else an aftereffect. At 3:51 a.m., just 4 minutes after the radio burst reached Earth, our planet's magnetosphere, the invisible shield of magnetic energy that protects us from solar radiation, had shuddered. At first, scientists thought it had to be a coincidence. Space weather disruptions happen regularly. The solar wind fluctuates. Cosmic rays strike. The magnetic field trembles under the sun's moods. But that night, the sun was silent. Every solar monitoring satellite, the Solar Dynamics Observatory, SOACE, showed a flat line. No flare, no mass ejection, no stream of charged particles. And yet the magnetometers didn't lie. From Alaska to Antarctica, every magnetic sensor registered the same blip, a precise, measurable contraction of the magnetic field, as though the Earth had been tapped by something unseen. It lasted 8 seconds. Then everything returned to normal. NASA's Goddard Space Flight Center ran the numbers backward. The compression pattern of the magnetosphere matched what you'd expect from a brief but intense particle influx, the kind usually triggered by solar storms. Only this time, the timing aligned not with any solar event, but with the arrival of the Andromeda signal. That was the moment when coincidence stopped being an option. Inside NASA's emergency briefing room, the lead physicist, Dr. Emily Chen of the CT Institute, spoke what everyone else was afraid to say aloud. It looks like Earth responded to the signal. For a long, quiet moment, no one in the room moved. It was a simple sentence, but it changed everything. Radio waves, by nature, cannot interact with a magnetic field like that. They pass through it harmlessly, the way light passes through water. The only way to cause such a distortion would be if the signal wasn't just radio, if it carried another, hidden component, something energetic enough to alter the magnetic flux itself. An electromagnetic pulse from a distant galaxy should have been impossible. The laws of physics say so. Yet here they were, staring at the data. They looked back at the first signal, the one from January 2024, and found a faint, almost invisible echo in the magnetosphere 8 minutes after it arrived. Back then, it had been dismissed as noise. But in retrospect, it was a signature. The same effect, just weaker. The first signal had been a whisper. The second was a shout. Now, everyone was asking the same question: if this is wave 2, when is wave 3 coming? NASA's AI teams were already running deep spectrum analyses. They didn't just want to detect the radio pattern. They wanted to decode it. If it was a natural signal, they needed to find the underlying physics. If it was artificial, they needed to understand its structure. The AI that detected the polarization flips had been fed every known astrophysical waveform: pulsars, magnetars, quasars, gamma, ray bursts, and even simulated black hole jets. None of them matched. So the system began digging into the timing, the pulses themselves. Each burst it discovered wasn't a single tone but a stack of overlapping frequencies, harmonics arranged in specific intervals. When translated into sound frequencies and slowed down, the signal produced something eerie, a rising and falling rhythm, almost musical, like a coded heartbeat. It was not random noise. It was organized. Then came the breakthrough and the horror. The AI found that the time intervals between each pulse formed a precise geometric sequence. Each silence between bursts was exactly double the one before it. 43 milliseconds, 86, 172, 344, the same ratio you'd find in digital binary systems, the mathematical backbone of computer communication. That meant the Andromeda signal was following a binary progression, the simplest and most universal form of logic, ones and zeros, on and off, pulse and silence. Every human-made digital technology, from computers to satellites, relies on that same structure. The scientists froze when the AI's confidence report printed on the monitor detected non-random pulse intervals. Confidence 99.94%. Dr. Chen, who had spent years debunking false positives in CTI data, simply whispered, "That's intentional spacing. Nature doesn't do that." But even that statement opened a new mystery. Because if it was intentional, who or what could send it? At this point, the signal had become more than just a cosmic curiosity. Governments were taking notice. The Department of Defense requested briefings. European agencies demanded data access. Within hours, the signal was classified under restricted communication channels. Meanwhile, NASA's Deep Analysis AI, nicknamed Prometheus, continued to crunch data. It didn't think in terms of curiosity or fear. It just calculated. And then, Prometheus found something no one expected. When the AI plotted the signal's polarization shifts, the tiny changes in how the radio waves twisted as they traveled, it found that the rotations weren't random either. They formed a pattern of repetition every 12 pulses. 12. That number repeated through the data 12 pulse clusters, each with the same internal symmetry. The AI's model visualized the pattern as a waveform lattice, and what it drew looked like a spiral rotating outward from a central axis. The visualization eerily mirrored Andromeda itself, a spiral galaxy. Could it be coincidence? Maybe. But the universe, in all its chaos, rarely repeats its art so precisely. As this revelation spread among the scientists, NASA brought in cryptographers and mathematicians, specialists who had previously worked on decoding deep space telemetry and encrypted transmissions. Their goal wasn't to find aliens. It was to determine whether the pattern could represent information. The team began testing for prime number sequences, Fibonacci ratios, and harmonic frequencies. In one section of the signal, they found a harmonic sequence that matched the ratio of hydrogen's emission frequency to that of deuterium, two elements fundamental to life and the structure of the universe. Was it a coincidence, or was it a message? One that used the most universal language in existence, physics. Outside the labs, the story began leaking to independent astronomers and amateur radio observatories. Rumors spread fast across online forums. NASA caught something big, Andromeda signal classified. WEV-2 confirmed. Officially, NASA remained silent. But internally, tension was rising. If the burst was truly that bright, 50 times stronger than the first and lasting 3 seconds, then the energy required was staggering. Scientists calculated that in those 3 seconds, the source released more radio power than the sun emits in an hour. That kind of power is beyond any known natural mechanism. Unless something new, something not in our physics, was at work. Some theorists proposed supermagnetars, neutron stars with magnetic fields so intense they warp space-time itself. Others suggested galactic core flares, a cyclic outburst from Andromeda's supermassive black hole. But those explanations had flaws. Magnetars don't repeat so precisely. Black hole flares don't produce polarized radio bursts this clean. Then came a theory that silenced the room. Dr. A.V. Loeb from Harvard, a veteran astrophysicist known for bold hypotheses, proposed that perhaps the signal wasn't a natural burst at all, but a technological byproduct, not communication in the human sense, but leakage, a side effect of something immense, a cosmic-scale energy transmission or even propulsion system operating 2.5 million years ago, a civilization harnessing energy at that scale, enough to make their signal visible across galaxies, would be what physicists call a Type 2I civilization on the Kardashev scale, a species capable of utilizing the full power of its star. And yet, Loeb's tone wasn't excited. It was somber. Because if that were true, that civilization was ancient, long gone before humans even walked upright. What we were seeing wasn't a message. It was an echo, a fossilized footprint in the electromagnetic sea of time. Still, some refused to accept that explanation, because something in the data didn't fit the echo theory. The pulse sequence wasn't just repeating, it was progressing. Each wave carried slightly altered intervals as if evolving or adjusting itself. That wasn't an echo, that was behavior. When NASA overlaid the first and second waves, a pattern emerged. A mathematical ratio between pulse intervals that formed a Fibonacci sequence. That sequence occurs in biological systems, fluid dynamics, galaxy formations, and notably, engineered designs seeking efficiency. The AI Prometheus didn't stop there. It analyzed amplitude modulations, the way the signal's strength rose and fell over time. When converted into a visual waveform, the amplitude pattern looked like binary encoding, 12 clusters, each representing a potential data packet. But data of what? Prometheus began testing digital translations, converting the wave structure into on-off patterns, then mapping those into mathematical sequences. The first coherent result appeared meaningless: 2, 3, 5, 8, 13, 21. A Fibonacci sequence, nature's code. To the team, it was the cosmic equivalent of someone knocking in a rhythm too deliberate to ignore. Outside the labs, global media began catching on. Conspiracy theories exploded. NASA hiding alien message. Andromeda pulse linked to magnetosphere flicker. Within a day, videos were racking up millions of views. Governments issued quiet instructions to avoid speculation. NASA's public statement was vague. We have detected an unusually strong fast radio burst from Andromeda. Analysis ongoing. But behind closed doors, the fear was growing. If this was a repeating signal, then logic dictated a third wave could follow. If it followed the same timing, every 18 months, then the next burst would arrive in July 2026. And if the energy continued increasing exponentially, it could hit levels capable of affecting not just the magnetosphere, but Earth's atmosphere itself. What terrified them most wasn't what they knew. It was what they didn't. Because somewhere in the data's final milliseconds, Prometheus had detected a subharmonic tone, an extremely low frequency component buried under the main pulse. A tone far below the threshold of normal detection, oscillating at exactly 7.83 Hz. That number might seem meaningless until you realize it's the same frequency as the Schumann resonance, the natural electromagnetic heartbeat of Earth's atmosphere. In other words, the Andromeda signal had carried a component that resonated with the Earth itself. Coincidence? Physics, or something that knew how to resonate with our planet. When that report reached the control room, no one spoke for a long time. The possibility was almost unthinkable. Dr. Chen finally said quietly, "Either this universe has physics we don't understand, or someone out there understands us better than we think." The room fell silent again. Outside, dawn was breaking. The telescopes kept tracking the faint glow of Andromeda 2.5 million years in the past, and every sensor on Earth was now tuned to listen for the next whisper, because whatever was sending those waves wasn't finished. And if the doubling pattern continued, the third might not just be a message. It could HEIMPLIKEIOMS. By the time the world reached mid-2026, the night sky had stopped feeling familiar. The stars still glimmered as they always had. But for those who knew, for those who understood the data buried under headlines and silence, every twinkle carried unease. Because somewhere beyond that field of light, across the black ocean between galaxies, something had spoken. And now, Earth was waiting for it to speak again. The Andromeda signal, as it came to be called, was no longer a classified anomaly. The leaks had grown too large, the data too widely shared. Amateur radio astronomers in Europe and Japan had confirmed the coordinates, while leaked telemetry from NASA showed identical spectral fingerprints. Governments were still denying its full meaning, but denial no longer mattered. The story was too big, too old, too deliberate. And there was one date circled in red across every major observatory in the world: July 7, 2026, the expected arrival window for the third wave. In the 18 months since Wave 2, the world had changed in subtle, quiet ways. Publicly, life went on. Traffic lights blinked, economies churned, wars simmered.